Hello, my little physics students, and welcome to Force Part 5, Example Problem. And so what I wanted to do is just kind of throw out a scenario here and maybe even throw in a couple of kind of different variables that we haven't looked at and analyze it from all the different angles of force, acceleration, mass that we've been learning in Chapter 3. Let's say we have a situation. Let's say that we have a couple more days like we did the other day, and it's just raining and raining and raining. And we've got some lovely ladies. Here they are. Let's call them Sarah and let's see. Here's another one. Let's call her Becca. Sorry about that. All right. And so, she needs arms. Oops, Sarah's arm got disconnected. Oh, there we go. All right. So here they are. Sorry. Yep. So anyway, so here's Sarah and Becca, and because the rain messed up her hair, I think. But anyway, so it's raining. It's pouring. Whoo, cats and dogs. And they say, "Oh no, we better get home. It's starting to flood." And so they run and they jump in their car. Ooh, here they are. So here's their car, right? And it's got a real big engine in front. And so there they are. They're in their car, and there's the two lovely ladies. But what happens is the rain is raising in the water, and the water's coming up. And it's coming up, and their car ends up underwater. So here, this part right here, this is underwater, okay? And they say, "Oh no, we're stuck, ah!" And so they're like, "Help!" So then a couple of other extremely smart, brilliant scientist guys, they come out, and let's say that. Their name, they're over here, and let's say that their names are, let's say, how about David and Enoch, right? Those are our brilliant scientists, right? So there's David, and there's Enoch, and so they come out of the school, and they see the girls. They've tried to drive through the water. And they're stuck, and they're going, "Help us! Somebody help us! We need some brilliant boys to save us." So they say, "Oh no, what are we going to do?" And Enoch says, "I know, I've got an idea." And David says, "Okay, what is it?" And so they say, "Let's drive over there and help them." And David says, "That's not going to work. Then we'll just get stuck." And Enoch says, "Oh yeah, right." And then David says, "Well." What if we got a bunch of lawnmowers and turned your car into an airboat so that it glided across the top of the water? And Enoch says, "Why use my car? Why don't we use your car?" And David says, "Because I don't have one." And Enoch says, "Oh yeah, right." So then they go and they get a bunch of lawnmowers, and they build and they take the lawnmowers, and so here's Enoch's car, and there's the wheels right there, right? And they take the lawnmowers, and here's a lawnmower, and they strap the lawnmowers underneath the car, and they strap one to the back, and they fire them all up, and it's shooting air down, straight down, and so they've got this cushion of air they're riding on, and then this lawnmower in the back, they've got a little cable to control that, and that's going to shoot air out that way. And so what they need to do now that they've grabbed lawnmowers from the neighborhood and they've built themselves an airboat, and the girls are still drowning, and now, of course, now the water is up to here, and they're going, "Oh no, we can't swim." And so then they're gonna drive their airboat over there, right? So let's say that their airboat with everything weighs 450 kilograms. It's a very small car, a smart car actually. It was Enoch. He had a smart car, and so they've got this airboat. It weighs 450 kilograms, And so obviously there's no friction with the car on the water, and so it's riding on this cushion of air. And so let's say that they're able to get this thing up to, they calculate up to a maximum of acceleration of 5 meters per second squared. And that's about how fast they need to go to get the airboat car that they've just designed over to help the drowning lovely ladies. And and so they're speeding along, and so then the question is, if there's no friction, how much force must this propeller exert on the air to accelerate the boat at 5 meters per second? So what we have going on here is how does this accelerate the airboat? Well, what's going to happen is this is going to push this way, and it's going to actually encounter air molecules, which are going to push back with the same force. And this is Newton's third law. So remember, anything smart in physics comes from Newton, right? Always remember that. So Newton's third law says that for every action there's an equal or opposite reaction. So we want to know, what is the force provided here? So if we can figure out the force here, we'll figure out the force that the air is pushing back on their airboat, and then we'll know what it's going to take, what force it's going to take to get them to go this speed right here. All right, so if there's no friction, how much force must the airboat? So let's figure this out. So this the net force is going to equal what? Well, so net force equals mass times acceleration, right? So the force net equals our mass, which is 450 kilograms, right? Times the acceleration that we're going to need here, which is 5.0. Okay. So what's that going to give us? Calculate that out, and you get, let's do significant digits, because we got 2 digits here. Let's go 2.2 times 10 to the third newtons. So that's the actual force that this lawnmower is going to need to push out in order to push that airboat, because that's the weight of the boat plus the 2 brilliant scientist-type young men. All right, so that was pretty easy. But what if we were to say that they do all that, but they find that their actual acceleration is only 4.95? Well, what caused that? Well, so they realized that that as they're going through the parking lot here, the wind and the air is hitting up against them, and so the wind and the air is causing a deceleration. And if they're only going 4.95, their calculations told them that they should be going 5. So what does that mean? Well, that means that there's actually a 0.05 meters per second acceleration in the opposite direction. So we could say negative 0.05 meters per second acceleration in the negative direction. And so then the question is, so what is the force of the air resistance, or the drag force, that is on this airboat as they go through? Well, this is also pretty easy. So what we're going to have to do is then just multiply the force equals mass times acceleration, right? So 450 kilograms is our mass times our deceleration of negative 0.05. And that's going to give us negative 22 newtons. So what's happening is, if this is the force in the forward direction, there's also a negative 22. So we got a negative 22 newtons, and we've got a positive 2.2 times 10 to the third newtons in that direction. And so then that gives us an overall acceleration of 4.95. So figuring out air resistance or drag force is fairly easy if you know the acceleration in the opposite direction. And you would know that by knowing what you're supposed to get and figuring out where you're at. Now finally, another thing that comes up a lot is the idea of force normal. Now force normal is, if I have a box and it's on the ground, that box is putting a force on the ground, and because that ground is holding it, it is holding it with an equal force pushing up. And that box's force on the ground is going to be the force of gravity, right? Which equals the mass times 9.8, because that's what gravity is doing. And so force normal is going to be the force needed to basically equalize force of gravity. So force normal is always the exact same amount as force of gravity in the opposite direction. So what is the force needed to hold this or to cause this airboat to hover, which is essentially the force normal. Now it's generated by these fans pushing down, and so it's going to be equal to the force of gravity. So it's pretty easy to figure that one out, right? So if the force of gravity is 450 kilograms, right, times 9.8, what is that going to equal? Well, that's going to equal 4.4 times 10 to the third newtons, which means that in order to cause this to hover, we're going to have a force in the exact same amount from these fans. And if we don't have a force in the exact same amount, if we have more, it's going to go up. If we have less, it's going to go down. So in order for it to hover, it has to be a force equal to the force of gravity pulling that down, and that should make sense. That will cause it to hover. Well, I hope this kind of helps to give you some examples of what we can do with analyzing situations and force, how we can figure out the force cause, the drag force, air resistance, or even the force normal. So in every situation, you have a lot of different forces acting on stuff. So hope that helps.